In addition to standard approaches for, let's say, standard and classical approaches for path planning, let's take a look to a little bit different approach. And it is shown here for curiosity and to highlight that there is still open field to propose different methods that have some benefits and nice properties. And in this case, it's a reaction diffusion models that are dynamic systems capable to reproduce autowaves, and autowaves represent a class of nonlinear waves that propagate through active media, and they propagate at the expense of energy stored in the medium, and for example, gas combustion. So reaction diffusion model describes spatial-temporal evolution of two state variables, for example, u and y, in space and time, and it is basically described by a system of nonlinear equations. And in this work, it is based on the Fitz-Nagumo model, which looks like this, and there are these parameters. And what is quite interesting for this reaction diffusion system is that the dynamics is determined by the associated Nurkin configuration, for which we don't we have the zero derivatives. So in the absence of diffusions, so which in this case give us these equations, and these Nurkin configuration have associated geometrical shapes. And just to briefly describe, so we have Nurkin configuration related to the steady state. So, and one Nurkin configurations are the stable states. So basically the Nurkin intersections represent stable states and unstable states, which is here. And it is a bistable system with a bistable regime. So the system, the concentration levels of these state variables u and v for each grid cell tends to be in a stable states if we have two of them. So what we can do is that we can modulate relative stability of both steady states. So there will be a preference. This is the steady state minus this is the steady state plus, and you can modulate the preference of steady state plus over the steady state minus. And so if we do that, then the system moves from one steady state to another steady state if a small perturbation is introduced. Okay, so and then the steady states are separated by a mobile frontier, a kind of traveling front wave. So these are the autowaves. So maybe now you will become a little bit more in the idea how this is used, and take a look to these cartoons. So the reaction diffusion based path planning is basically a computational model where we use finite difference method on Cartesian grid with direct boundary conditions for description of the dynamics of this reactive diffusion model. So we have this external forcing, which is the interaction of additional information in our setup, is that we constrain concentration level to some specific values. And what we also did here is that we propose two-phase evolution of the underlying reaction diffusion model. So there is a propagation phase where the free space is force set to steady state minus, and the start location is forced to steady state plus. And as I described previously, the system is, when we introduce the perturbation, the system tends to steady state plus. So this is the front wave propagation through the media. There is the nonlinear systems underlying, but quite important here is this property of non-annihilation property of the front wave, of the autowave, which has been described by Alejandro and Professor Munoz. So, and once we start propagation, so it's like front wave, we terminate the computation once the front wave reaches the goal. So that's easy to compute. And now we switch the system we consider a different nucleons, and now the start and goal positions are forced to be steady state plus, and steady state minus shrinks until the only path linking the force points remains. So this is the contraction phase. We switch the system, different parameters, and the system tends to be in a steady state plus, which represents a path. So this is a computational model of the reaction diffusion system, but there is a nice property, and maybe you can see that. Okay, so this seems to be quite smooth, and we can also somehow control what is the clearance between the path or this steady state and the obstacles. And these are the examples of the found wave, and using the wavelength of the up to waves, we can control the, and with combination of the size of the computational grid, we can control the clearance, so the paths are safe. In comparison to distance transform, Werner diagram, and reaction diffusion systems, you can see, okay, this is nice because that seems to be smoother, much smoother than distance transform and Werner diagram, and has some clearance. So it's completely different approach, but can be beneficial. Okay, take a look for this example. Okay, that's the propagation, and now this is the switching the phases, and we have a path. So, to be honest, this is relatively demanding, computationally demanding, but it has the benefit that if we have such a real map that is captured by the sensors, and it contains some noise, the auto waves is actually able to deal with this noisy. And if you try to use other methods like this distance transform with this noisy, so you can post-process the grid map, or you can actually apply the reaction diffusion planner. So this is just to show, okay, there can be multiple approaches, and even very unconventional and weird methods may provide some benefits. So let's summarize the lecture on path planning. It's relatively comprehensive. So we covered the path planning methods and notation of the configuration space, specifically important for exam and any other usage of especially the sampling-based methods. We go over the geometrical map representation methods using shortest path road maps, Werner diagram, cell decomposition. We take a look to artificial potential field, distance transform, kind of front wave propagation. We mentioned graph storage planning, where the standard graph storage can be employed like A star, but there are other variants like jump point search and theta star, and that can speed up the switching process significantly. There is also a relation to the grid path planning, that the path can be smoothed using some simple path simplification or theta star-like algorithms. What is important when you deploy the robot in the real environment and you don't have up-to-date map, so you update the map once you execute the mission, so you can reuse the previous search results in algorithms like D-star or D-star Lite. And for curiosity, there is unconventional reaction diffusion based planning, and we will continue on our robotic information gathering with a focus on a simple mobile robot exploration in the next lecture.